Swayam Prabha. Digital India. Educated India.
So, in my previous lecture, we have discussed about the pseudostatic analysis for seismic slope stability. Now, we will continue that pseudostatic analysis here also. You can see for a particular slope how we can incorporate these two forces. One is HV, the vertical force, and another is the FH, horizontal force. So, that two forces are basically the seismic force. So, it has been converted to equivalent static force, and then that two force has been applied, and here you can see how to calculate the resisting force and the driving force. Here basically this W, here this value is basically N into tan phi. So, CL is the cohesion part and N value is this is N, and this one is the T. So, what is how we will calculate the N value? N value we can take the your component of this W minus F in the normal direction, normal to this failure surface, that will be W minus FB cos beta, normal to this one, and the horizontal, if I take FH in this N direction, FH component, that will be negative minus FH sin beta. Similarly, for this T direction, this will be W minus FB sin beta plus this will be FH cos beta. Okay, so that's why this is driving force and this is resisting force. We will get the factor of safety. So now generally this FH has more or the significant effect as compared to FV. You can see that in the this is here the FH is been subtracted. So, it is subtracting this your resisting force here. So, that means it is reducing the resisting force, this FH, and but here FH is been added in the denominator. You can see FH is been added. So, it is actually increasing the driving force. So, it means reducing the resisting force and increasing the driving force. So, that means it will basically reducing the factor of safety. But if you see the FV is reducing this value in both the cases. So, I am not saying that this effect is 0, definitely FV has the effect, but the FH has more significant effect as compared to FV. So, that is why in sometimes this FV effect is been neglected. So, FV is taken as 0. Okay, only FH effect is been considered, but it is not mandatory that always you have to put FV equal to 0, but you can consider the effect of FV, but FH has the significant effect as compared to FV. It does not mean that FV does not have any effect. It has the effect, you can consider it, but FH has significant effect as compared to FV. So, now the selection of pseudostatic coefficient. So, this is the coefficient of pseudostatic acceleration or the pseudostatic coefficient. So, selection of pseudostatic coefficient. So, there is no such proper rule to select the pseudostatic coefficient. So, Tarzaki suggested KH value should take 0.1 for severe earthquake and KH equal to 0.2 for violent destructive earthquakes and KH equal to 0.5 for catastrophic earthquakes. Okay. So, that means the range of KH is 0.1 to 0.5. So, as the Tarzaki has suggested. But the seed observed that 12 dams, those are required a minimum factor of safety of 1 to 1.5 for k is equal to 0.1 to 1.1, 0.1 to 0.12 after analyzing 14 dams. They have analyzed the 14 dams and they found that if they consider k is equal to 0.1 to 0.12, then the minimum factor of safety can be observed for or was observed for 12 dams. So that's why their suggestion you can take KH value is 0.1 to 0.12. Or there is another suggestion, the KH value in between 1/3 to half of Amax by G. Amax, how I will get the Amax, you know, that is already been discussed, how the Amax or PGA or PHA you can get. So that KH recommendation is, it is 1/3 to half Amax by G. And another recommendation is that you can take the KH value half of Amax by G. Okay. So that would be produce very large deformation for dam. So that means there is not any proper guidelines. So, but it range is 0.1 to 0.5, that as per the Tazaki's suggestion. But how much KH is you taken? So generally, if you don't have any other option left, you can take KH is equal to half of Amax by G. Okay, that is the last recommendation, half of Amax by G, which is the similar to the previous recommendation also. It is 1/3 to half, so half of Amax by G. Okay, but that is you can consider. Now, if I solve one particular problem of slope stability, that you have a slope and there is a failure surface of the slope. Okay, and okay, so this is the this is circular slope, and this one is the radius of the circle. So this is R, which is 28 meter. Okay. Now this slope has two layers are there. This is my layer 1. This is layer 2. Okay, the properties are this layer, this is C equal to 0, 30, C equal to 30 kPa. Then phi is equal to 0 and unit weight is 18 kilonewton per meter cube. For layer 2, C value is 50 kilonewton per meter square, phi value is 0, unit weight is 19 kilonewton per meter cube. Okay, and this slope, its area is been detected or area is been determined. The centroid of each failure mass is been determined. That means you can take small segment. Okay, here it is small segment, and then you can add those area and you can calculate the centroid of based on those small segment with respect to the O. O is your center, and then it is given this is the centroid, that is A, and this is for the second layer, this is B. So this may be not as per the scale, but this is the position of the A and B two centroid, okay, of these two failure mass, because we have two layers. So now the this distance of this centroid, these two centroid, for A from this central line it is 3 meter, this B, and for this A it is 12 meter. Okay, and for this is horizontal distance. So from the O, the vertical distance will be, say, for the A, the vertical distance is 14 meter. Okay, and for the B point, the vertical distance is, say, 22 meter, and radius is 28 meter. So now here we have W1 weight and W2. Okay, so first we will check the slope under static condition. Okay, so now our KH is taken as 0.15 and KV is taken as 0, but you can consider KV value also, but here it is taken as 0.5. And what are the values are given? The area for A, it is 165 meter square. A means you can say this A zone. A is the represents the failure mass of the layer 1 and B represents the failure mass of the layer 2. Okay, so A area is 165 meter square and B area is, say, 270 meter square. Similarly, the length, this failure surface length in the layer 1, this zone, this A zone length in the layer 1 is, say, 6 meter. I mean, this length is 6 meter. And for B failure mass, the length is, you can see, it is much larger compared to the zone A. So that is 51 meter. Now we have to check the static factor of safety, then the seismic factor of safety. So for the slope stability, say, first we consider the section, then the W, which is kilonewton per meter, then the moment arm, which is in meter, in the static moment, which is kilonewton meter per meter. Okay, static moment. So for the section, say, A, W will be, how I will calculate the W? Area is given. Okay, how I can calculate the W? Area is given. So this is 165 into the unit weight. Area is given into the unit weight. Unit weight is 18. Okay, so that area is 2970. This is kilonewton per meter, is the weight of your section A or the failure mass in the layer 1. And the moment arm will be, because we are calculating the overturning moment. We are calculating the overturning moment. So overturning moment, this means this W. So momentum will be from the, we are taking the moment with respect to O. So momentum will be 12. 12 is the moment arm. So the static moment will be 12 into 2970. So static moment is coming out to be 35.64 into 10 to the power 4, that is for section A. 10 to the power 3. 10 to the power 3 for section A. Similarly, for section B, your unit weight is 5130. Momentum would be, this momentum will be 3 meter. This is the momentum, because W is acting, we are taking moment with respect to O, that is 3 meter. So this will be 15.4 into 10 to the power 3. So the total static moment for overturning moment, this one 51.04 into 10 to the power 3 kilonewton meter per meter. So this is overturning moment. Now I will calculate the resisting moment. So again I will take the section, then the length in meter, then the cohesion value in kilonewton per meter square, then the force, that is kilonewton per meter, then the momentum in meter, then the moment, kilonewton meter per meter. So for section A, length is how much? 6 meter. Cohesion value is 30 kPa. So force will be here along this length, this cohesion is acting, so that means here it will be 30 into 6. So this 4 will be 180 kilonewton per meter. So it is along this length, that force will act in this value surface. This is 180. Now momentum, if I take the moment with respect to O, so this is a circle and this is the radius. So momentum will be the radius of the circle, that will be 28. So the moment will be 180 into 28. So this will be 180 into 28. So this is equal to 5.04 into 10 to the power 3. Clear? So here similarly how it is coming, this is 2970 into 12 actually. So now for the section B, the length is how much? 51. Cohesion is 50. So this is force is 2550. Again momentum will same because the same circle. So this will be 71.40 into 10 to the power 3. So the resisting moment, total resisting moment will be 76.44 into 10 to the power 3. So I can calculate the factor of safety for static. That is your resisting moment divided by the overturning moment. Resisting moment is 76.44 into 10 to the power 3 divided by 51.04 into 10 to the power 3. So it is coming out to be 1.5. Static factor of safety is coming out to be 1.5 for this particular problem that we have taken. Now we will do the seismic analysis here, and we will incorporate the seismic forces. How will you incorporate that? Because your kV is equal to 0. kV is taken as a 0. So vertical component, that FV, that we will not consider because kV is 0. So FB is also 0. We will consider only the horizontal component, that is your KH into W2. Here also I will incorporate this pseudostatic force, that is KH into W1. W1 and W2 is the weight, and it will act the centroid of this each failure mass. Now because of this KH and KH, these two forces, KH into W1 and KH into W2, our resisting moment will not change. It will remain same. it will, because resisting moment is same here, only the overturning moment will increase. Okay, so we have to consider some additional moment due to overturning. So that we will calculate. I will calculate that. So we will calculate the, we will extend my overturning moment table. Moment calculation. So we will add few more columns. So which is that kh into w, that is in kilonewton per meter. Then moment arm for this kh into w, and pseudostatic moment. That is kilonewton meter per meter. So kh into w, the for your, if I say section, if I write section again, so this is A. So W1 was 2970. So kh will be 0.15 into 2970. So this is coming out to be 445.5 kilonewton meter. Momentum, what will be the moment? Now this force, initially W was acting in downward direction and kh into W1 is acting in the horizontal direction, because this, you can take this direction in the other side also, but this is the worst condition, because if we consider this, because seismic force will come left to right, right to left, it can come. So we can provide, now we are providing this direction because it will give you the worst condition, worst the lowest factor of safety if you consider this direction. Clear? So now here it is will be, initially when we calculate W1, that time the momentum was 12. Now the momentum will be horizontal, so it will be 14, because this is the 14 is the momentum. So I can write the momentum is 14. So moment, pseudostatic moment will be your 5.5 into 14. So that will be equal to 6.24 into 10 to the power 3. Similarly for B, the kh into W 0.15 into 5130. So this is equal to 769.5, and the momentum is here. This is the momentum 22. Initially it was 3 for W2 calculation, now it is 22. So this will be 22. Okay. Now my pseudostatic moment will be 16.93 into 10 to the power 3. Now if I add them, then the total pseudostatic moment will be 23.17 into 10 to the power 3. So the total moment will be the pseudostatic moment plus the static moment. So now the factor of safety for static plus seismic, or considering the seismic forces, it will be the resisting moment will be same as the static case, 76.44 into 10 to the power 3. But the overturning moment, that will increase. Initially it was 51.04 into 10 to the power 3. So that will act. In addition to that, a pseudostatic moment is being incorporated or will act to 3.17 into 10 to the power 3. So the factor of safety is 1.03, or which is close to 1. So you can see initially in the static condition, the factor of safety was 1, okay, 1.5. Now that factor of safety will reduce to 1 if I consider this seismic force. So, this way we can get the factor of safety. But one more thing, that here when we are talking about this, how to calculate this considering the pseudostatic analysis, it is very simple analysis, but it has some limitations also. The limitations is that here the time dependent effect is not considered. Even in some cases that it has been observed that in the pseudostatic analysis, it is showing this, it is safe, factor of safety is adequate, but still the structure failed. So, till the structure failed. So, that is why this method is simple method, but so many things is not been incorporated in this method. This time dependent effect is not incorporated and other things are not been incorporated, but still it is been used because of its simplicity, and it will give an idea, okay, that what would be the current status of this structure under seismic condition, that it will fail or not, or if it will safe, then how much safe it is. So, it will give an idea that, and you will get an idea that using this approach, that whether what is the status of that particular structure. Now, the another thing is that in pseudostatic analysis, it will give you the factor of safety. That means whether the slope is your safe or not. I mean, it will safe under static condition or the seismic condition, it is safe or not. That idea will get, but it will not give us the deformation of that slope. Okay. So, for example, that if we have a slope, and this is your failure surface, or this is the, oh sorry, so this is the say failure surface. Okay. So, this is the failure surface. So, this is the failure mass, or this is the sliding mass, you can say. And here, if the seismic force is acting, okay, this is the slope, say. So, now here you can see that if your acceleration, you are applying this earthquake induced acceleration, that if it is just in such acceleration is applied, that your factor of safety is equal to 1 or it is greater than 1, then what will happen, that your this failure mass will you slide, it will also accelerate, because if it is because factor of safety is less than 1, if you are providing an acceleration where the factor of safety is less than 1, say 1 means is just sliding will start to initiate the sliding, and if it is less than 1, then obviously there will be a sliding of this mass. Now, how much it will slide, that information will not give that pseudostatic analysis. So, for that information, the Newmark has proposed a Newmark sliding block analysis. So, I will discuss those things in the next class, that what is the Newmark sliding block analysis and how I will determine the deformation or permanent deformation of a slope by using this technique. So, that we will discuss in the next class. So, remember that that if your factor of safety is greater than 1, then this sliding will not take place. Okay, so this sliding will start when the factor of safety is less than 1. Clear? So that means the factor of safety at which, or the acceleration at which your factor of safety is 1, then that acceleration is called yield acceleration. I mean, here in my previous problem, you can see that your static and seismic factor of safety, when I consider the your seismic load, the factor of safety is 1. That means I have here considered the KH is equal to 0.15, and KH is what? KH is equal to AH divided by G. Okay, so that means your here KH is equal to 0.1. So that means here your H is equal to 0.15 G. So I can say my yield acceleration here is 0.15 G. So my yield acceleration here is 0.15 G. Yield acceleration is what? Which acceleration? That acceleration at which the factor of safety will be exactly 1. So now if your applied acceleration is less than the yield acceleration, then this sliding will not take place. So sliding will take place if the applied acceleration is greater than the yield acceleration. Then the sliding will take place, and in the next class I will discuss by using this Newmark sliding block analysis how we can determine this amount of your deformation. Thank you.